Hello, everyone. Today we're going to be talking about beta regression, and this lecture serves as a supplement to the content we're going to discuss in class. In order to talk about beta regression, we need to discuss the beta distribution. And we talked a little bit about the beta distribution last week when we talked about Bayesian data analysis. In that context, we worked through a kind of hypothetical example where we were looking at the proportion of dog people in a random sample. And we were looking at different prior distributions. And a good prior distribution for a proportion is the beta distribution. So this week, I want to expand upon that and talk a little bit more about the beta distribution. And in order for us to do that, we need to talk about shapes, mean, and precision parameters. Then what I want to do is walk us through an example. So we're going to use an example that looks at reading accuracy, dyslexia, and IQ. And what I want to do is highlight how we can fit that model, interpret the parameters, and visualize that data. Then I want to spend a little bit of time talking about other types of beta models. These are models that don't these are models that don't quite fit within kind of the traditional beta distribution. So for instance, if we have data that's exactly 0 and 1. So I want to spend some time talking about the 0-1 inflated beta as well as the ordered beta. Here I want to talk about these models conceptually. So we're not going to talk about how we, fit these models and interpret the parameters. But hopefully you can use the information that we've learned throughout the semester to interpret those parameters on your own and ask questions if needed. As always, these are the packages that I'll be using for this lecture, so make sure you have these downloaded and installed, and then you can follow along in RStudio by downloading the Cordo document at this link. So in psychology, rates, proportions, and percentages are quite common. A lot of us are using this in our research. I know a lot of us are using accuracy as an outcome measure. I know I use that a lot. Or some of you are maybe using test performance or final test performance. So how do we analyze that data? So it's quite common, and all of us have probably done this, is to take that data, that accuracy data, for example, and just throw it into a linear model and interpret the results that way. However, today I'm going to highlight an alternative to the general linear model approach, and that's beta regression. And in order for us to use beta regression, we're going to need to understand the beta distribution. So the beta distribution is perfect for things like rates, proportions, and percentages. And that's because it's a continuous distribution that takes numbers between 0 and 1. However, it's important to note that it cannot take numbers that are 0 and 1. So the beta distribution is a continuous distribution that takes values between 0 and 1, but are not 0 and 1. That's important. And at the end of the lecture, I'll talk about alternatives that we can use if this is your data. So the beta distribution requires two parameters, shape 1 and shape 2. I don't know who named these, but it's very non-intuitive, but shape 1 and shape 2 controls the location, spread, and skew of the distribution. And I have a variety of different distributions or beta distributions depicted on the right-hand side here. And what I've done is I've created these distributions by just changing the shape 1 and shape 2 parameters here. So we can see that we get some distributions that look normal in shape. We get some distributions that are positively skewed or negatively skewed. So there's a whole variety of different distributions that we can create by changing these shape parameters here. We could get inverted U shapes, we can get U shapes, etc., etc. So let's talk a little bit more about these shape parameters so we can build up a more intuitive sense. So let's work through a concrete example. So let's say that I have some final test, and on this final test there are 10 questions, and each question is worth 1 point. So the exam or the final test is worth 10 points. And let's say that most people score 6 out of 10. We can take this 6 out of 10 and we can reformat it as an equation, right? So the number correct as the numerator, and then the number of correct plus the number incorrect as the denominator here. So we get 6 divided by 6 plus 4, which is 10, so 6 out of 10. And we can reformulate this yet again by using A and B. So number of correct is A, and divided by A plus B, where B is number of incorrect. And we can map this A and B notation onto shape 1 and shape 2. Shape 1 is going to be A, which is the number of correct, and B is the number of incorrect responses. So A here deals with successes, B here deals with failures. So let's go ahead and plot this beta distribution. So that's what I have here. This is the code that you can play around with to produce various beta distributions. So in our particular example, the shape 1 parameter, which is the number of successes, is 6. And then the shape 2 parameter is number of failures, which is 4. So let's go ahead and run this. We're using the d-beta function from R that allows you to create various distributions. The d-beta function allows you to create beta distributions. So let's go ahead and run this code here. And this code creates a beta distribution. And this should look familiar to you from last week. But we can see here that the beta distribution here is kind of centered at 0.6, which is what we scored on the final test. But what's important to note here is that when shape 1 is greater than shape 2, the distribution is shifted towards 1. If shape 1 was less than shape 2, it would be shifted towards 0. So we can go ahead and play around with this, and let's just say that we got 4 out of 10. So we have 4 successes and then 6 failures here. Let's see how the distribution changes when we change the shape parameters here. So again, we see here now that the distribution has shifted towards 0. My recommendation is for you to play around with these shape parameters so you can build up kind of an intuition about the distributions. So the shape 1 and shape 2 parameters are not really that intuitive. So instead, it's common to use mu and phi. So mu is the mean and phi is the precision. So we can actually formulate shape 1 and shape 2 as a combination of mu and phi. So A is just mu times phi, and B is 1 minus mu times phi, where the mean is just A divided by A plus B, and phi is A plus B. So we can rearrange these things. And we could take the mean and precision and calculate the variance, and the variance is mu times 1 minus mu divided by 1 plus phi. And what's important to note here is that the higher phi we have, the lower variance we have. So there's going to be a narrower distribution. But if we have low phi, that means that there's going to be higher variance. And that means that we're going to have a wider distribution. So these are the basics of the beta distribution. So hopefully you kind of developed or intuited a sense of the beta distribution. So now let's talk about the beta regression. Typically what I want to do is show you how to fit a beta regression model, interpret the coefficients, and visualize the data. To run a beta regression, we're going to be using the beta reg package and the beta reg function, and we're going to run a frequentist version of the beta regression. In class, Branson's going to show you how to run a Bayesian version of the beta regression. So let's go ahead and run this line of code here to load in our library. We're going to be looking at data from the beta reg package, and this comes from Smithson and Verliken from 2006. And this data set has 44 data points from 44 Australian primary school children. The dependent variable is going to be accuracy. This is a score on a reading test. I'm not sure what the reading test is, but it's just reading accuracy. And then we're going to be looking at 2 independent variables. Dyslexia, so are the children diagnosed with dyslexia, yes or no? And then the IQ score. This is a nonverbal IQ score that's z-scored. And we're going to be interested in looking at the interaction between these 2 variables. So let's go ahead and read in our data and see what it looks like here. So we have our accuracy column here, which goes between 0 and 1. We have dyslexia, so was the child diagnosed with dyslexia, yes or no, and then the IQ variable. Let's run that again. And then let's go ahead and deviation code our variable. So if individuals are not diagnosed with dyslexia, we're going to label them as negative 0.5, and if they are, 0.5. So let's go ahead and see what that data looks like to make sure that we did that properly, and we did here. Awesome. Let me go ahead and rerun these lines of code. So what's quite common is to take this accuracy data that we have and to perform an ordinary least squares regression on it. So as a first step, let's go ahead and run a linear model on this data. So what I have depicted here is the summary output for our model. And looking at the coefficients and the significance, we see that dyslexia is statistically significant, the IQ variable is not statistically significant, and the interaction is not statistically significant. Let's go ahead and look at the diagnostics or the assumptions checks to see if we violated any of those important assumptions for the ordinary least squares regression. So using the check model function from the performance package from the Easy Stats ecosystem, these are our assumptions checks, our diagnostics. First, looking at the posterior predictive check here, which looks at the relationship between the data and the model. We see that the model and the data do not align properly. There's a misfit here where we're expecting a normal distribution and we don't see that normal distribution here. We almost see something that looks like bimodal here. So that's problematic. Linearity, we want this green line to follow this the reference line. It looks okay, nothing to be that concerned about. Looking at homogeneity of variance, so this can test heteroscedasticity. We see that there does seem to be some heteroscedasticity in our model here. We want this reference line, the green line here, to be flat and horizontal, and that is not the case here. So it looks like we have some heteroscedasticity in our model. There doesn't appear to be any influential observations in our data. There doesn't appear to be any multiclinearity. Looking at the normality of residuals, our residuals do not seem normal. It looks like almost like an inverted U here, right? We want these residuals to fall on this green line here, and they don't, right? So models that use proportions or probabilities or ratios usually violate the important assumptions of ordinary least squares regression. There's asymmetry, so it's not normally distributed. It's not symmetric, and there's also heteroscedasticity. So linear model doesn't seem to be a good model for this type of data. So what do we do then? Well, we use a beta regression. Here, we're going to model accuracy using a beta distribution, which we've discussed with two parameters, mu and phi. And we're going to model these parameters separately. So there's going to be a mu part and then a phi part. And then the actual model we're going to fit is very similar to, a generalized linear model here, where on the left-hand side, we're going to apply a link function here. And we're going to use a logit link like we've used in logistic regression. And the purpose of this logit link is so the values of mu fall between 0 and 1. Fitting a linear regression model, we know that predictions can fall outside the 0 and 1 bounds. So by applying the logit link function, we get estimates or predictions between 0 and 1, which is what we want, which aligns with our data. So let's go ahead and fit a beta regression model. So when we're using the beta reg function, we're going to have to fit two parts. We're going to fit a mean part or a mu part and a phi part or a precision part. And this is what the pipe is for. So on the left-hand side of the pipe is going to be our mean components here. So we're modeling the interaction and predicting accuracy. And then the left-hand side is going to be the phi part of the precision part. Here we're just looking at phi of dyslexia and IQ. We could also put in the interaction if we wanted to, but for our purposes, I'm just going to use the plus sign here. So we're not modeling the interaction. And we're going to use the logit link. There's other link functions that we can use, like the probit, but for now we're just going to use the logit. So let's go ahead and run that model here. And let's go ahead and take a look at the summary of the model. So this looks similar to the other outputs that we've seen before, right? So what we have here are two components here, right? So as I said before, we're modeling the mu part, and then we're modeling the phi part or the precision part here. And we have estimates for both parts of the model. And then we're using maximum likelihood here. So let's go ahead and parse out each of these components and explain them a little more. So first, let's go ahead and talk about the mean part of our model here. And I'm using the model parameters function, and I'm using this conditional argument to get the mean for the model. So this is our summary output here, and what's important is that these coefficients are on the logit scale, so always remember that. But what's good about that is that we can interpret this like a logistic regression. So these estimates represent the log odds, and we can take the exponent and get the odds ratios if we wanted to. But what I want to draw special attention to are the significance of these effects. So if you recall from the linear model, there was a significant effect of dyslexia, but there wasn't a significant IQ effect or interaction effect. Now that we fit a beta regression model, we see that there's a significant effect of dyslexia, a significant effect of IQ, and also a significant interaction between dyslexia and IQ here. So we see that the beta regression is actually more powerful than a linear model here. The second part of the output is going to be the precision output. And I'm using model parameters here again, and we're going to specify the argument as precision to get the precision output. What's important to note about the precision output is that it uses a different link, and it uses the log link, similar to a Poisson regression here. So the parameters are on the log scale, and what we can do is we can take the exponent and we get back the original metric. And that's what I have highlighted here because I set the exponentiate function or the argument to true, and then that's what we get here. So similar to the logistic regression, the logit or the log odds are kind of unintuitive, right? So what we're going to want to work with in the Bayesian or in the beta framework is predicted probabilities. I haven't seen a lot of beta regression models in the literature, but it seems fairly common to not interpret the log odds, but interpret the probabilities. So that's what we're going to do here. And we can use our marginal effects package in the average predictions function to get the predicted probabilities for our condition. So we can see here, these are probabilities. So we can see for the control group, which I've labeled as negative 0.5, they have a higher accuracy on reading than the dyslexic group here. We can also calculate average marginal effects or risk differences, and we can use the average comparisons function to do that. And that's what I have highlighted here. So I have the risk difference for dyslexia, so the difference in probabilities between the two conditions, and then I have the average marginal effect for IQ. So how do we interpret these? So for the IQ parameter, for a 1 unit increase in IQ, there's an increase of about 2 percentage points on reading accuracy, or 3 percentage points. And for dyslexia versus control, it seems that dyslexia decreases reading accuracy by about 25 percentage points. And both of these are statistically significant. We can also do model comparisons like we've done with other models that we fit. So here I'm comparing a model that has an interaction to a model that doesn't have an interaction term. And we can use the test likelihood ratio function to assess those two models here. So I just ran those lines of code. And what we can see here is that the chi-square statistic is significant. So what that means is that a model with an interaction is warranted, right? So we shouldn't be fitting a main effects model, we should be fitting an interaction model. We can also use the likelihood ratio test in lieu of the summary output. So we can use the ANOVA function, and which will calculate a likelihood ratio test, and we can look at the main effects and interactions. And again, there's a main effect of dyslexia, a main effect of IQ, and also a significant interaction between the two. And it's important to note here that we're using type 3 sums of squares because interactions are important. So the interaction is statistically significant. So what we can do is we can follow this up with a simple slopes analysis. So we can compare the average marginal effect at each level of dyslexia. And we can use the average slopes functions to do that, where I have the variable as IQ and then by dyslexia. So we're going to look at the control group versus the dyslexic group here. So I have that highlighted here. And we see for the control group, the difference or the average marginal effect is about 0.10, and that's statistically significant. If we look at the dyslexic group, the slope is not statistically significant. So it is 0.05, so it's right on the threshold, but it's not lower than 0.05. So we're going to say that's not statistically significant. So as a write-up, we can say for those with dyslexia, an increase in IQ decreases reading accuracy by 2 percentage points. However, this is not statistically significant. For those without dyslexia, for those in the control group, reading accuracy improves by 10 percentage points for every unit increase in IQ. Visualizing this using the GGM means function, and also using a new theme here, which I think is pretty cool, called Theme Blackboard. We can see that for the control group here, negative 0.5, I should have probably labeled these better, but I didn't. Again, we see that as IQ increases, so does accuracy. But for the dyslexic group here, we don't see any changes between IQ and accuracy, right? So it doesn't seem that IQ, nonverbal IQ, and accuracy are related to dyslexia here, or there's not a relationship for the dyslexic groups here, which is kind of interesting. So I've kind of ignored the precision parameter or the phi parameter here, but we could also do model comparisons to see if we need those phi for each variable. So that's what I'm highlighting here, where we're fitting a model that has those phi for dyslexia and IQ, and comparing it to a model that does not have the phi for each variable. Here it's going to fit just one phi parameter here. Whereas in the first model here, we're fitting a phi parameter for dyslexia and IQ. Here, we get a statistically significant chi-square test, so that suggests that we do need to have the additional phi parameters for dyslexia and IQ. The beta regression is really useful when we have outcome variables that are between the intervals of 0 and 1. The beta model, or the beta regression model, breaks down when we have exactly 0 and 1 in our data set. So let's go ahead and look at our reading skills data set to highlight this. So looking at our reading skills data set, we can look at the accuracy column, and what we can observe here is that there is no zeros or ones in our data set. So let's go ahead, but there is these 0.99. So let's go ahead and change the 0.99 to 1. So that's what I have highlighted here. So basically we're just changing accuracies that are 0.99 to 1. Let's go ahead and take a look at that to make sure that. Okay, so we've changed these to 1 now. So let's go ahead and run our beta model. And what happens when we run this beta model, when we have accuracy equal to 1, we'll get this error that says invalid dependent variable. All observations must be in between the interval of 0 and 1. So what do we do about this? So what we could do is we could do something similar to what the authors did of the reading skills data set and just change the ones to 0.99. So we can just slightly modify those values. So if we had a 0, we could change it to 0.01. And then just run the beta regression model. That's not recommended because there's alternative models that we can use that seem to work pretty well. So what I wanted to do is spend a little bit of time talking about 2 of these models that we could use. One is the 0-1 inflated beta, and then the other one is the ordered beta model. And unfortunately, we can't fit these models in a frequentist framework. A lot of these tools have been developed in the Bayesian framework. So what I wanted to do was kind of talk about these models conceptually at a high level. So we're not going to go through explicit examples of how to interpret the parameters explicitly, but hopefully I can give you some introductory information that if you're going to use these models, you should be able to build up from those. So one type of model that we can use if we have zeros and ones in our data is this 0-1 inflated beta. And situations in psychology where we have zeros and ones in our data is quite common. So a lot of folks in psychology use slider scales like the one that's depicted here, where individuals take this little slider and they move it along this continuum. And usually these are converted into zeros or ones or between 0 and 100. So those values are converted. I use this type of data in my research. So I do some meta-memory research. And one of the questions I ask individuals is on a scale between 0 and 100, how likely is it that you're going to remember this particular word, right? In that particular case, we have lots of zeros and we have lots of hundreds in our data set. So if we were going to visualize this type of data, we might see something that looks like the histogram on the right-hand side here that I have my mouse scrolling over. So we can see in this histogram that there's lots of zeros and there's lots of ones here. So the 0, 1 inflated beta can be used to model this process. And this is conceptually related to the 0 inflated Poisson model, where we are modeling several different processes. With this 0 inflated Poisson model, we model 2 processes. So it was a mixture model. Here we're modeling 3 processes. So when using the 0, 1 inflated beta, what we're going to do is first, we're going to fit a model that is basically just a logistic regression model. And this model is going to predict if the outcome is either 0 or 1. And we're going to compare that to not exactly 0 or 1. And we usually call this parameter ZOI in the BRM function. The second process we're going to model is also going to be a logistic regression model. And this is going to predict if the 0 or 1 outcomes from above are either 0 or 1. So we can say that this is kind of the 1 inflated part. And we're going to use the COI parameter, or it's going to be called the COI parameter. And then lastly, we're going to model the mu and the phi here. So for the third process, we're just going to model this beta regression model. So we're going to model the interval between 0 or 1, but not exactly 0 or 1. And this is just going to be our beta regression. So on the right-hand side here, I have some example syntax that we can use to fit these type of models. This is very generic here, but hopefully you can take this and modify this to fit your purposes. So there's a new function here, and that function is BF. And this basically makes the BRM function a little bit more flexible because we can fit more complicated models and more parameters here. So that's what I'm using this particular function for. But what I have highlighted here, the first line is going to be modeling the mu part of our model, or the mean, right? So we can model the outcome or the mean as a function of the covariates or the predictors. The second line is modeling the precision. So we can model phi as a function of the covariates or the predictors. The third line is going to model the ZOI parameter, or the 0 or 1 inflated part of the model, where we're comparing 0 or 1s to not exactly 0 or 1s. And then the last parameter we're going to model is the COI parameter, which is the 1 inflated part. The data is whatever you called your data set. And then in the BRMS package, there's lots of different families we can use. And here we're going to use the 0, 1 inflated beta. So what I have highlighted here is just some sample output. So this should look very familiar to us. We fit Bayesian models last week using the BRMS package. And this is very similar output here. So the family or the metadata at top, we're using a 0, 1 inflated beta. And then we have our link functions here. So mu is a logit link, phi is a log link, what we just went over. And then the ZOI parameter is a logit, and the COI is the logit parameter. And then we have our formula. And then we have our population level effects here. And hopefully what you'll notice here is that for each parameter, there's an estimate. So for phi, for ZOI, for COI, we have an estimate. So hopefully you can see that this can grow very, very unwieldy if we have lots of factors or lots of variables in our model. And as a result of this, it could take a really long time to fit. So as a solution to this, we can use what's called the ordered beta regression. So as I just stated, the 0, 1 inflated beta can be really complex with lots of parameters to estimate, and this could take a long time to run. So the ordered beta regression was developed by Robert Kubinek, and this was developed very recently. And this is a special case of the 0-1 inflated beta. And essentially what it's doing is it's combining ordinal regression and beta regression. And this simplifies the whole process. And the package that will allow us to run this ordered beta regression is this ord beta reg package. So we can go ahead and load that in if you're following along. And the ordered beta regression essentially models 3 different processes. So we're going to model exactly 0. This is called cut 0 in the output. We're going to model somewhere between 0 and 1. This is our beta model. And then we're going to model exactly 1. This is our cut 1. So 1 and 3 above are modeled as ordinal logits. And then 2 is modeled as a beta logit. And this can be interpreted similarly to a beta regression while also taking into account those 0s and 1s. So we're modeling the whole process. But using this particular model simplifies the output a great deal. So I have the syntax that we can use to perform this model. So we're going to be using the ord beta reg function. And then we're going to use the bf function again to fit our model here. But we don't need to. We could just delete this and we can just fit it like a normal model. But here we're fitting a dv as a function of an iv here. We have our data. And what I want to point out here within this particular function is there's this true bounds argument here. And this is set to 1 to 32. So what I want to highlight here is that we don't have to have exactly 0 or 1 type of data. We don't have to have 0 or 100 type of data. We could have something where we have something bounded between 1 and 32. We have those extreme ends, right? 1 and 32, which I think is really cool. So on the right-hand side, I have some example output here. So hopefully we can see here that the output is extremely simplified, where our population level effects, we don't have several parameters we're estimating now. We have our intercept and we have our variable of interest. And then we have family-specific parameters. So we have phi, which is our precision parameter that's fit. And then we have these cut 0 and cut 1 points. These are going to be our ordinal logits. So that's how these can be interpreted. And what we can do, if we're interested in, we could probably model the cut 0 and cut 1 points to see what variables predict these extreme values here. So there's potential for some flexibility here. But hopefully you can see how something like this can simplify the process a lot. And it seems like the ordered beta does a pretty good job of fitting the data. So just to kind of summarize everything, beta regression seems to be a really good choice to model things that psychologists care about, like percentages, proportions, and ratios. So we shouldn't be using things like linear modeling to model these type of data because we have beta regression. And even if we have exactly 0s and 1s in our data set, alternatives exist. So I talked a little bit about the 0-1 inflated beta and the ordered beta regression within a Bayesian framework. So there's alternatives that exist that can help us model that type of data. Unfortunately, there's not a lot of examples using these kind of models, at least in psychology. But hopefully this has given you some food for thought. And if you're interested in using these type of models, hopefully this has kind of given you a foundation to help build up your models and build up some intuition about the estimates from your models.